Okay, video 10 out of the Schneider TM3 series. Today we're going to be looking specifically at how to wire for negative logic on TM3 expansion modules that have both inputs and outputs. So it's a specialized module that has got both the I/O on the same module. But before we do that, let's just deal with this term IEC negative logic. We're going to start with a caution statement over here because negative logic is dangerous on both inputs and outputs if it is used with a DC supply that has a grounded negative. And this is the important term over here. If your negative is grounded, then there is some potential danger that can go and happen. If the negative is not grounded, then it's just as safe as using positive logic. However, since a lot of times negatives are tied together inside of a plant type of situation, it can be difficult to track down, or in some cases, even the power supplies themselves automatically come with a grounded negative. So yeah, we'll deal with that inside of the video. Really, the big danger from this stems from the fact that my inputs can basically be seen as being triggered. We'll get a danger from unwanted PLC triggering during a ground fault on those cables, and my cables out to my loads could accidentally just go and operate as well. So since we don't want to have loads operating, outside of the control of the PLC, nor do we want to have inputs operating without the actual input device, it could just create some dangers. And we'll take a look at those and we'll simulate those faults later on in this video. Before we finish looking through there, we just need to go over what sourcing and syncing themselves are. Sourcing is going to be direct connection of my positive to my common terminal that I'm going to go and have. Syncing is going to be direct connection of my negative to my common terminal. And for both IEC positive and negative logic, both are going to go and be used, but on separate sides of the PLC. So we'll look at that, which would be IEC negative logic, which is using the negative to activate something. So if we bring a negative into an input, that would mean we'd already have to have the positive tied in. So we would have a sourcing input. And if we're bringing a negative out through an output to a load, that would mean that we would have to have a syncing style of output. And once again, as we said before, if that negative is grounded, a ground fault could activate either one of those. Usually I use this memory trick for any of my classes and students. When in doubt, which is going to be safest, go with the positive logic, and this memory trick helps you remember what you want. You want to have syncing on the inputs. See the IN and the IN in those words. You want to have sourcing on the output. But that's not what this video is about, because there will be times and places where you do need to go and use that negative logic. So we'll go through it and we'll explain how to properly wire for it. First of all, let's take a look at which module we're using. We're going to be using inside of here the TM3DM discrete. It's going to be a module that's got both IOs on it, inputs and outputs, 8, and then it's going to be an R or a relay style. What we cover inside of here can also be expanded out to the larger one, the DM24R. That is also going to be available. And they're both fantastic cards because you've got the option to do IOs on them. Really, for anybody that's running multiple of these Modicon PLCs, you should have a couple of these in your storeroom, because if you have a faulted card, you can swap out and get back to operation either, line or load until you can order in the proper cards, but usually you can just kind of limp through off of some of them. Okay, let's take a look at our data sheet for it. The data sheet for this specs that we can go and utilize this card specifically on the 221, 241, 251, and the 262. We do see that the inputs do conform to the IEC 61131. That's our governing overall standard that we use for anything to do with PLCs. We can use them as syncing or sourcing on the inputs. Today we're going to take a look at them specifically for sourcing inputs. And we see that they're going to be rated for 24 volts with a 7 milliamp input. So they don't take a lot of current to go and operate. Our outputs are going to be a relay style. We can go and use them as either positive or negative logic on the output. And the output is going to be rated for 24 volts DC or up to 240 volts AC. And the reason that the DC is much lower than the AC is because a DC current is much harder to interrupt than an AC current. Do note as well the way that they have written out the current rating for this. That's 2000 milliamps. We would commonly in the trade refer to this as a 2 amp output. For whatever reason, it's just been written as 2000 milliamps. That's the maximum current that you're going to drive through any one of these relays. They give us a little bit more information, both the inputs and the outputs, on the second part of the data sheet. And the things of note that we really do want to take a look at are going to be these over here, the voltage states that are going to be guaranteed. And what they're doing for us is they're telling us where we have got a safe range of voltages that we can go and use. They say that the voltage of state 1 guaranteed starts at 15 volts. In other words, anything that is going to be above 15 volts is a guaranteed high, a logical 1 that we would have coming in there. We see as well that there's a voltage state 0 guaranteed, which is going to be anything that is going to be 5 volts and below is going to go and be a logical 0. And what that leaves us with is this section over here, which we refer to as the undefined range. And the undefined range doesn't mean that it's not going to do anything. It just means that there's no guarantee that the manufacturer can make as to whether a voltage that is coming in there is going to go high or low. So if you take in some garbage voltage, remember you're supposed to be using 24 volt, but if you take in, 11 or 12 volts, that 11 or 12 volts could potentially switch high, or it could potentially switch low because you're bringing it into the undefined range. So just don't bring in voltages that are not going to be proper for what you're looking for. Watch that on all of these, and they do give you guarantees for these high and low states for them. Response time for my outputs over here is going to go and be 4 milliseconds to turn on, 4 milliseconds to go and turn off. The maximum current for the entire group is going to be 7 amps. We're going to stick them at 2 amps apiece and 7 amps as the group. And the total number of cycles, the mechanical durability we see is going to be 20 million cycles. That's on-offs that we can have out of these relays. When they're talking about that, they're talking about as well just the total number of mechanical operations. This is not necessarily going to be dealing with passing current through. You pass heavy currents through there, you're not necessarily going to be able to make that full 20 million operations. They're talking about the physical operations. Okay, now we're going to move on from there into our installation sheet. Inside of our installation sheet, you're going to go and locate the module by its module number, and then they give you 2 separate drawings for the same module. And what they're doing on these drawings is they're showing 2 separate types of logic. This whole first one here is going to go and be my IEC positive logic. Positive, I'll just write that as positive IEC over there. That's not what this video is about. That's actually all covered in video number 9. So if you want to do IEC positive logic, go to video number 9. This video over here is going to be about this side over here, which is showing all negative logic. And to be honest, you could use both syncing inputs and syncing outputs, or sourcing inputs and sourcing outputs, or something like that. That would be perfectly fine as well, but it's pretty uncommon for anybody to switch streams like that. All right, let's take a look here at our inputs. We see that the first set over here is going to be 0, 1, 2, 3 as our inputs. We got a common that we are going to go and have. And then we've got this over here, which is an NC. NC does not stand for normally closed. It means no connection or not connected. Write that out like that. In other words, there's no lines that are going to be brought into that NC section. Looking up top over here, we see that we have got a positive being brought to the common. That would mean that this would be a sourcing set of inputs. Let's write that over here on the side like that. Which means that since our power supply has got a positive brought in, we're going to go and have a negative then that is going to get carried around. That negative gets switched into each of my components, and then ultimately it's going to go and travel through the logic on the inside, completes the path like that. So it's a sourcing style that we see. On my outputs over here, we see that we have got the negative that is going to be connected from my DC supply to my common. Disregard this over here. This is just going to be showing us options that we could use it with AC. You're either going to be using DC or you're going to be using AC, never both simultaneously. So when you're dealing with these diagrams, you have to kind of ignore one and only look at the other one. We see that the positive for this one is being brought up here, and then that they're subdividing that down into each of my individual loads. So each of my loads gets a constant positive brought to it. We do see one master fuse for the entire group. We do see individual fuses for the individual loads over here as well. And then what we see is happening is that that negative is getting switched through my relays on my outputs. That's what's happening inside of here to be taken to that load. And when we take a look at this, we should be able to always trace a complete path for current all the way through my load, through the input card, and back out to my supply. And we'll do that when we're doing our wiring on these ones later on. Couple other things that we want to just take a quick look at while we're on this diagram over here. These symbols over here are going to be for fuse holders. We're going to talk about those briefly. And then these symbols over here going around my loads. If you take a look at the notes that are on your installation sheet, they do talk about using suppressors or snubbers or some other form of arc attenuation, because if you're using DC and you're switching that through here, you're going to go and get inductive kick. You get that collapsing magnetic field from your coil, and it's going to try and discharge. What you don't want to have it do is try to discharge across the contacts, the relay contacts inside of there, while this is opening up, because then you're going to result in, destruction of those contacts. Instead, what you want that to do is go through one of these. And so let's just take a quick look at one of those looks like. That would be one of these over here, a suppressor module. And you'll note that's a very small component. It's hard to tell the scale off of here, but relatively small. 2 brass pins that are going to be coming off of it. You see the symbol over here is a back-to-back Zener diodes, and it's rated for between 24 through 250 volts DC. It's going to go and attenuate any sort of arc that we would have from inductive kick. They're very small. They install on the side of a contactor like this. You can see the way that they show that the pins, these 2 points over here, are going to get brought up into the back side of the coil. That's where your coil is housed inside of the contactor. It's kind of an angular view of a contactor over here. You push them in and then you lock them up against the side. And what that does is it leaves this out of the way. It takes up no extra room on your DIN rail, but now this coil itself is going to be able to go and discharge through this path with its inductive kick. Put them on. They are supposed to go and have them. You will get, operation, and it'll be decent operation. In a lot of cases, smaller relays do have built-in suppression, but if in doubt, and particularly when using a larger coil, like on a contactor, make sure that you've got something set up for this. Fusing is usually going to be done through the use of DIN rail fusing. These are going to be fuse holders mounted onto your DIN rail. You got one of 2 styles that are quite common. First one over here is going to take class CC fuses over here. If you do use that, use it with HCLR, which are going to be a very fast-acting style of fuse. The other one is going to be the smaller glass or ceramic fuse bodies that you can go and utilize DIN rail mounted as well. Both of these do have indicating lights on the surface that are going to let you know when you've got a blown fuse inside of one of those holders. So pick one, whichever is going to work. The manufacturer's data sheet does usually recommend class T fuses, which are extremely fast-acting fuses. However, they are not easy to locate fuse holders for, nor are they easy to necessarily find the fuses for. And so it can be tricky in the field then, because when the customer does, have faults on their field wiring and they blow the fuses, they can run into these issues where they then just bypass your fusing because they can't find something proper. So work with systems that are available where you are. Here in BC, these are relatively common, so either one of these would be a great option. Okay, now we are on to our wiring for this one. We're just going to take a quick little zoom in here on my PLC section. What we see over here is that we have got a TM3DM8R MESE, so it's a 251 family. This is going to be my main PLC. We've got the card that we're looking at, the TM3DM8R, that we have attached onto here. And if we look at the card, we see that the card has got a breakdown on it. It shows that we have got DC inputs that are able to go in there and RY output, in other words, relay outputs. And then we've got that NC, or not connected, component that's going to be in the middle over there. Zooming back out off of this one here, we can just follow our path for power in. We see that we're feeding AC into this cabinet. That AC goes through a DIN rail fuse holder and feeds into a DC power supply. That DC power supply converts it down to 24 volts. And then from there, we can go and feed it through to these 2 fuse holders. This fuse holder over here feeds power to my PLC, so it's just going to be controlling the main brain of that PLC. This fuse holder over here is the one that we are going to be working off. We also see that we have got 2 types of devices here. I've got input devices, that's going to be those 2 push buttons, and I've got output devices. I've got a contactor and a pilot light that we are going to be utilizing for these ones. Okay, so since we are working with negative logic, we'll go IEC Negative Logic that we're going to be working with over here. That means that my inputs need to be sourcing. In other words, my inputs need to have a positive brought over to them. Now, on the manufacturer's data sheet, they did not show, and we'll just skip back to that one really quickly, they did not show any fusing on what we're bringing into here. We are going to go and provide fusing on the positive that's going to come into the common over there. So we'll go back this way, and we're going to take our power off of here into the common. So now we've got our common tied in. We're going to go and take a positive out of there that we are going to go and switch up to my devices themselves, running through there. I guess you could say take a positive out of there or take a negative into there, whichever one works for you. We'll take the negative in right now to my devices. So that's going to be taking a negative up, and we're going to go and drop it onto here and onto here. And then all we need to do is run the actual leads from here down to my input. So we'll take one from here and we will take one from here. What we will now have is a complete path for current flow. We'll go over top of that and just highlight it through. We'll see that we've got positive that we can go and carry along here through my DIN rail fuse holder, through the input card, through and up one of these onto my negative and all the way back to my power supply. So you've got a complete circuit. You're going to go and have operation out of this one. The next part that we're going to have to do is going to be my outputs. My outputs are going to be syncing style of outputs. So if we're going to be dealing with those, they did show multiple fusing off of those as well. We'll just skip back to that one over here. They do show that we are just going to have our negative connected to the common, that's syncing, and then that the positive comes through a single fuse holder, and then it subdivides down into other fuse holders they suggest you have per load. It doesn't always happen that you're going to have individual ones per load, but at the very minimum, at least have this one over here, and that's what we're going to apply. We are not going to go and use individual ones per load, mostly just for the sake of drawing to keep everything nice and clean. Okay. Back to where we were over here, we're going to go and take a negative to a common. So we're going to just run out of my DC power supply over here, down, and we have now got a negative attached into the common. It's kind of hard to see with the black on black over there, but it's a negative into the common, so we've got a syncing style of output. What we're then going to do is we're going to go and take a positive to my individual loads. So we'll take this one around here, we'll drop it into the A1, which is the coil of my contactor, and we will drop it into the positive on my pilot light like that. And then the last thing that we're going to do is we are going to go and run back our actual output. So we'll take this A2 from here, and we'll bring that one in right there, pick a terminal, we'll pick 5 for that one, and then this one over here would be done in the same manner. Take it from here, and we'll run this one into terminal number 4 over there. Perfect. So at this point now we have got a syncing set of outputs. Once again, we're just going to trace through, make sure we've got a complete path for current flow. So from our power supply, we've got our positive going through my DIN rail fuse holder over there. We can see that we bring a positive up to my load. We'll go through this contactor over here. We can run the positive through the coil, and then from the coil back to my PLC card. It goes through the card and back along my negative to my supply. So we have got a complete path of current all the way through. Operationally, we're good to go. Now let's just talk about those dangers that we talked about before. The big danger is if your negative is going to go and be grounded. So over here, we're just going to go and attach a big ground strap between the negative of my DC power supply, and we're going to attach it onto one of these DIN rail ground buses. They attach to the back plane, so the whole thing, attaches and grounds together. What our danger is now going to be is if we end up with a ground fault off of any one of these lines over here, we could go and get operation off of any one of these lines. And we'll do these one at a time. Let's start with this output line that we are going to go and have over here. We're going to say that this line gets faulted right over there. As soon as that line gets faulted over there, even if this contact inside of here is off, so the load is not called to be on right now, but we ended up with a pinched cable that is out there, what we will get now is we'll get positive that can feed all the way through. It can hit my coil, go through my coil, travel along here, and then it can go and jump out along that ground fault, travel through your bonding system, travel back up and in. And at that point, what we see is that we would have a complete path for current, and this coil would be energized. That's the danger with your IEC negative logic and with a grounded power supply. Let's go and take a look at what would happen on an input over here. Same deal, we're going to go and say that we've got a ground fault that's going to go and activate. So we'll take this one right over here. We're going to say that that cable got pinched somewhere out in the field. And if we go and track through, remember, we're not looking now at the device, we're looking at the PLC, and we can go and track through a positive. We could track through that we could have a positive that would be able to travel through my input card now and complete its path back to the power supply. So at this point, even if this push button itself was not operational. I guess I should have probably done on the normally open one here, but even if whatever this device is not operational, there's going to be a complete path for current through, which means that you are going to go and have this input over here, which is going to go and light up here. We'll light up that light over there. It's going to show that as being a high input, even if the field device itself is not activated. So obviously this can be dangerous, if the buttons or sensors or whatever it is are not pressed, but the PLC thinks it is. It could be overriding an end stop. It could be starting up components when people are in the way or things like that. So be very careful. Neither of these two faults would exist if the DC is ungrounded. If the DC is ungrounded and if this cable faulted or if this cable faulted, as long as that negative does not get tied to ground, there's no path back through there. All right, that's the end of the IEC negative logic.